Hello, everyone. I hope you are keeping good and keeping okay. And I hope everything is going well out there for you. I know that it's been very long. I have not made some videos. I have not made any video actually for you guys. But I'm so happy that the video that I already have on the channel is still, making impact, helping people to get a job. So, we can only improve on what we have and keep making video to ensure that there's a perfect understanding in what we do. So, yeah, I'm happy to be here once again or come your way once again today. So I have received some questions of some things that people want me to talk on, and I'm going to be talking about one of those things now. Okay, so yeah, let's move into that. Right. Before we continue, my name is Dr. Emmanuel Obodo. I'm a senior biomedical scientist, and I'm also a lecturer in biomedical science here in the United Kingdom. I'm HCPC registered, and of course, I'm a fellow of Institute of Biomedical Science and a fellow of Higher Education Academy. Okay, fab. So just before I continue, just in case if you want any support and you want me to support you in anything that I could professionally, please feel free to email us at twogoodconsultant@gmail.com, or you can check our website, which is at twogoodconsultant.co.uk. Okay, all right, that's by the way. Let's get into that. So we are going to be looking at understanding linearity, especially when it comes to pathology laboratory. Understanding linearity when it comes to pathology laboratory. So now the first thing we are going to do is to try to have a perfect understanding of what this linearity actually means. If you look at this very graph, you are going to see that I called it analyzer comfort zone. So the secret here, which of course I have actually made a video on calibration curve. If you understand calibration curve, then you should be able to understand linearity. Okay, so because they work hand in hand. So when you say linear, it means that there's a straight line. Okay, there is consistent with a measurement. Okay, so when you say that something is linear in this context, you are saying that what I've gotten is within the expected target. Okay, let's say for example, think about your standard. Okay, your standard curve, as the case may be, which is actually what the linearity of course means. So before you run a test, okay, you have to do the quality control. And your internal quality control, you can have level 1, level 2, level 3, as the case may be. So each of those very control has been manipulated to give you a result that is within a specified range, okay? So now, what it then means that that internal quality control samples, that modification is to make sure that they continue to fall within the analyzer comfort zone, within the targeted ranges of that very analyzer. Okay, that is actually what linearity means. So therefore, when you get a result that is outside the comfort zone, in other words, when you get a result that is outside the concentration of what the analyzer should actually give you, when you get a concentration that is outside the concentration that you can rely or depend that analyzer has given you a good result, that means that result at that time has fallen outside the linearity. We're going to make this clear. So if you look at this, I started by saying that it is analyte method that produces result, which that result is directly proportional to the concentration of the analyte. The analyte there is talking about maybe your sample. In your sample, let's say you want to measure bilirubin, or you want to measure hemoglobin or white blood cells or PTNR or APTT. It doesn't matter. Anything that you want to quantify. It can even be maybe in immunology, something like HCG, as the case may be. Okay, so any concentration of something that you want to measure that is in the sample, that is the analyte. So when you now use that analyte method to be able to get a result that is directly proportional to the concentration of what you are analyzing that is in that very sample, within, and that is obtained from a specified range, that is what linearity actually means. So maybe I should put it in my own words, okay? So just see this way. Let's say that you are measuring a bilirubin, for example, and that bilirubin gives you an absorbance of 0.9. That 0.9 is not the concentration of that very bilirubin. That is not the amount of the bilirubin that the patient has. But what is giving you is the absorbance. So linearity means that the analyzer would then have to carry that absorbance and check it against this 0.9 absorbance of bilirubin. Where does it fall under the concentration of the linearity of that straight line? Okay, the sensitivity, the comfort zone of that very analyzer. Okay, once it has done that, then is linearity. So when you talk about linearity, it means that the analyzer has gotten a result, and that result it has to now work it out within that very straight line. And once it work it out within the straight line, wherever it fall, it can now give you the concentration. Okay, that is linearity. So once you obtain a result that is consistent with the concentration that the analyzer have within its specified range, okay, that means it's linearity. So what it then means is that if you do get a result that is outside that very range, let's say for example, the comfort zone of the analyzer is between let's say 50 to 200. Okay, what that means is that if I get an absorbance, for example, I get a measurement, think about anything. Okay, what the analyzer will say, let's stick with that bilirubin. Let's say I got absorbance of bilirubin of 0.9. So maybe from that 0.9, when you match the 0.9 to the target of, for example, between 50 to 200, it might fall, that 0.9 might fall under 80. Okay, within that very straight line, because the straight line should give you what the absorbance is and also should give you what the concentration should be. So the concentration, which we are going to look more as we progress on this video, okay? So the concentration is underneath. You can get whatever thing that you are measuring here. So the absorbance can be here and the concentration is here. But what is important is the fact that any absorbance that you get should be able to narrow down and give you a concentration. If the absorbance becomes too high or too low, that is outside what is a specified range of that very analyzer, or the comfort zone of that very analyzer, or outside the curve, which is a calibration curve. What did they mean? That for the fact that the analyzer cannot quantify the absorbance of what is measuring and give you a concentration that is reliable, because sometimes the analyzer might give you a result then, but then it's trying to tell you that this is outside the linearity. Okay, sometimes an analyzer can actually give you a result, but prompt you that this is outside the linearity, or it might say that it has failed the linearity. What it's saying is that because I have tried to work it out, this is what I'm able to give you. Therefore, you can't trust that result, because the analyzer giving you a result and prompting you that this result is outside the linearity is trying to tell you that it's not reliable. I don't know if that makes sense, okay? So because what is reliable when we are giving a result out has to be that result has to be consistent within the range of the linearity of that very analyzer, within the comfort zone of that very analyzer. Let me repeat this again. So you have absorbance here, you have concentration here. So if you get absorbance, let's say 0.9, that 0.9, which is your absorbance, means something when it comes to concentration. So when you check it, when the analyzer now take the 0.9 absorbance, it will work out which concentration is it. For example, it might be 80. Then the analyzer can then give you 80, okay? And that 80 becomes the value of whatever thing that you are measuring. Now, remember I said we're taking an example that the target, the specified range of that very analyte is between 50 to 200. So if the absorbance of 0.9 fall under 80, that is linearity because it's within the target. But let's say you get absorbance of, let's say, 10 point something, and that 10 point something means it's bigger than 200. What the analyzer will do that by the time you take the 10 point something and he found out that he can't get the 10 point something based on the comfort zone of the analyzer, there's no 10 point something absorbance. Maybe the absorbance end with maybe 0.6. End with maybe 6.0, for example, but you are getting 10 points. Now, for the fact the analyzer has exhausted all the absorbance, exhausted all the concentration, it cannot give you a reliable result. If it tries to give you a result, it will prompt you that this result is outside the linearity. So what do you have to do then? Which I'm going to talk more. So anytime a result falls outside the linearity, okay, I have received, I think, there was a time I was analyzing, that was full blood count, and I noticed that the white blood cells has fallen outside the linearity. Just the white cells, others were okay. Now, because it has fallen outside the linearity, what do you think I have to do? Okay, so what I would then have to do is to dilute it. The same thing they do with bilirubin. If they, let's say a baby that is jaundice, okay, especially in the terms of maybe hemolytic anemia, as the case may be, okay, hemolytic disease of the fetus of the newborn. So let's say that baby is highly jaundiced. So what is going to happen is that the absorbance that baby sample will give, that highly bilirubin sample will do that, it will exceed the comfort zone, the sensitivity of the analyzer. Under that condition, is going to fail the linearity. So what a good biomedical scientist would then do is to dilute that very sample. So you are diluting the sample so that you can bring the concentration back within the specified range that is consistent, that is directly proportional to what has been saved or what has been recognized or what the analyzer has been recognized that is reliable when giving a result. I hope that makes sense. So that is why many analyzers that I've used, okay, whether in biochemistry or hematology, coagulation, as the case may be, will allow you to set, in fact, I was actually doing a test recently. I think the D-dimer was so high, so I was not able to get a result. What I did was to ask the analyzer to do a further under clotting factor. Now what we now need to do is to give it more time to give you the result. Okay, so let's say for example the result was supposed to be given within maybe whatever, maximum supposed to be 300 seconds, and at the end, if it exceeds that 300 seconds, I can say, okay, I want you to go as far as 600 seconds. That is giving it more time. Now if you come to biochemistry or maybe food block count, so what you are going to do then is to say, okay, dilute this, maybe 1-in-1 dilution or 1-in-2 dilution. Even in coagulation will do that, do 1-in-1 dilution, 1-in-2 dilution. Why are you doing 1-in-4, 1-in-5? So you are telling the analyzer to keep diluting it until the result can fall within that specified range. Does that make sense? So when we talk about linearity, we are saying that the analyte, the sample, what we are measuring on the sample is within, the result obtained is within the specified range, okay, that is consistent with the analyte measurement. I hope that makes sense, okay? So now, if you look at this, you're going to see that analyte method, we'll now look at this y-axis, look at the x-axis here. This is where the concentration is supposed to be. So when the analyzer gets a result, let's say the absorbance here, it will work out from this absorbance, what concentration is it here? Then it can give you the value. But if it check the absorbance and it is outside it's outside this very linearity, it means that it has failed that linearity, and what you then need to do is to dilute it. So to define linearity is a method of measuring an analyte that help to produce a specified result, which that result then is directly proportional to the concentration of that very analyte over a specified range. So the key word there is over a specified range. Therefore, anytime the result is outside that very specified range, it then means that it has failed the linearity. I think that should be clear by now. Okay, all right, fine. Now, this is also another way I want to explain this, just to help us to have a better understanding. So you can see these are concentration, these are absorbant. I just want you to have that understanding. So this is a standard curve. The same thing is applicable here. So what you really want when you do a calibration, you really want your arrow square to be as close as 1 as possible. In fact, if it is 1, that is even perfect, okay? So maybe 0.999, like as you can see here, or 0.98 as the case may be. But, you really want it to be as close as 1 as possible. So this is what we mean by linearity. This is also what we mean by linearity. So I want you to also see linearity, that even though it can signify straight line curve, but if you look at this one is not really straight. It's maybe something like hyperbola, I would say that this one is. But for the fact that these points are within the range, the targeted range, that is still linearity. So when you look at linearity, you are looking at, okay, any result that you can look at here now, the highest result it can give you is around maybe 4,000 something. This is where this stop. It's not up to 5,000, okay? So the highest absorbance you have is 2.0, if that makes sense. So what it means that if you now get a result that is within 2.0, you can get a concentration. That means it's within the linearity. But if you get absorbance of 2.5, 2.2, it cannot, because once the analyzer take that 2 point something, there's no 2 point something. here is just 2.0. So the analyzer will be unable to give you a concentration that is proportional to that 2.2 or 2.5, because the highest sensitivity or the highest comfort zone of this analyzer is 2.0 absorbance. Does that make sense? So what is going to do that, if it gets something like maybe 2.5, it might still give you a result, but it's going to flag maybe it failed the linearity, or it might say outside linearity. So once it said outside linearity, it's now up to you as a biomedical scientist either to automatically set it up on your analyzer to do maybe 1-in-1 dilution or 1-in-2 dilution, as the case may be. Why are you diluting it? You are trying to bring the concentration to be between these very absorbance, so that it can be able to give you a specified concentration. Because once you get absorbance within this very range, any concentration it gives you is reliable, because your quality control is measuring within this very absorbance and within this very concentration. Does that make sense? So once you get a result outside what is comfortable with, once you get a result outside what outside its specified range, it will give you a result that has failed a linearity, and you will then have to dilute it. Okay. If you look at this as well, that's what I'm trying to say, that if you've seen my video on calibration curve, you are going to see that this is also the same thing here. This is a calibration curve, and you want it to be as close as one as possible. Again, look at it. This is absorbance, okay? So the highest absorbance here is about 3.5, okay? Then you can see the concentration as the case may be. What this then means is that any result you are getting that is within this very, up to this very 3.5, you are going to get a result that will give you a concentration. And that concentration is going to give you, we are not talking about whether it is abnormally high or abnormally low or normal. No. At this point, we are talking about that the result we are getting is consistent with the analyte, with what is in the sample, is consistent with the patient. Does that make sense? So even if the result is high, for the fact that it is consistent with the patient, that is fine. Does that make sense? So now, if you get absorbance that is, let's say, 3.5, that is high, obviously, but the result is going to give you, even though it is high, is what is consistent with that very patient. So what I'm trying to explain here is the fact that when we look at linearity, it covers the low aspect, the normal aspect, and the higher aspect. It covers low abnormal, normal, and high abnormal as well. But what then happens if you get a result that is drastically high outside its comfort zone? It cannot give you a result. If it does give you a result, it will tell you that this is outside linearity, and then you have to do something about it. Does that make sense? Okay, so that is why when we talk about linearity, like I've mentioned, you are trying to determine a patient result or analyte result. You are trying to determine a result using this very specified range, okay, which is within this place to that place, or within this absorbance to that absorbance. Does that make sense? Okay, so that is what linearity actually means. Hopefully that helps. Okay, now let's look at why is this linearity, why is it really important? It's important because, remember, I've just explained it already, that the reason, the whole essence of this is to make sure that the result you are obtaining is consistent with the patient, is consistent, is reliable, is reproducible, okay? And the only way it can guarantee that it's reproducible is that the result you are obtaining have to fall within the concentration, within the comfort zone of that very analyzer. Does that make sense? Okay. Now, so it helps to produce accurate patient result, and it gives confidence in the reportable range. Does that make sense? That is why, like I mentioned, if you now get a result that is outside the reportable range, that means it has given you a result outside the linearity. You then have to dilute it. Now, maybe I should actually say this, or maybe I should say it at some point, that you dilute the result does not mean you are not going to give accurate result. It helps you to work out the actual concentration. Maybe I should give you an example. If you do 1-in-2 dilution, okay, let's say but the analyzer will calculate it for you anyway. But let's say in manual terms, if you do 1-in-2 dilution, then when you get a result, you have to multiply it, basically. Okay, all right. So it helps to reliable clinical decision, because it can help the clinician to be able to make a decision that can benefit the patient. Of course, it's compliance with ISO 15189 requirement, and overall, it ensures patient safety. So the whole essence of making sure that we get a result that is within the linearity is for patient safety. Very important. It's for accuracy. It's for confidence and all of that. Okay. Now, let's look at when it fell, what could make linearity to fail. Remember, I did mention, maybe if I should go back just to show you, okay? Remember, I did mention that you want your calibration to be as one as possible. So imagine that whoever that did this calibration saved it or accepted this calibration when it was maybe 0.8. That is wrong. It is wrong. Should I say that is wrong in a way that it did not increase the sensitivity, the comfort zone of the analyzer. The more the calibration curve, the arrow square is close to 1, the more you are increasing the comfort zone or the sensitivity of that very analyzer. Does that make sense? So when calibration is not properly done, that can make the linearity to fail. So calibration problem, okay, reagents start deteriorating or instrument limitation, okay, maybe we're not following the maintenance or monthly maintenance or weekly maintenance or quarterly maintenance, as the case may be. Once there is an error, systematic error somehow, okay, that can lead to linearity start failing, okay? So this is the possibility why linearity fell. Now, it could also be due to pipetting error, and it could also be due to detector saturation. This detector saturation is actually where I think most of the linearity, I know the other ones can also be the case, happens. For example, do you remember I mentioned to you that the analyzer can only give you a result of what is comfortable for. So if the analyzer is not comfortable of the absorbance that is getting, comfortable here means that the result is getting is outside is linearity. That means it's not comfortable with it. That means it's not able to, it's not saturated. The ability to measure a reliable result is not saturated, okay? Therefore, though it might give you a result, but that result is giving you may not be accurate because it's outside linearity, it's outside its linearity, and that is detector saturation, meaning it continue to wait. The absorbance is higher than what it would have wanted to detect. Okay, that is actually one of the primary reasons why linearity also failed. Okay, that's by the way. Now, I have used this just to make it clearer for us. So when you look at this very green zone, that is linearity. When you look at a red zone, that means that is outside linearity. That means it has failed the linearity. So this was exactly what I'm trying to explain. So when you get a result and you work out the concentration, for the fact that it is within this very green zone, are you getting me? That is linearity. Because it's within the straight line. That is linearity. It's within the comfort zone. That is linearity. Does that make sense? So the result you are obtaining, the result you are reporting is within the specified range, okay, that is consistent with the sensitivity of that very analyzer, which is linearity. Does that make sense? But imagine that your result is now coming outside this green, which is a red one. It means that it has failed the linearity. I hope that makes sense. Okay. Right, so I decided to give us example to help us to understand this better. But before we dive into this very example, please don't forget, if you have not subscribed to this YouTube channel, please subscribe, and of course help us to share, like, and comment. Okay, let's continue. So imagine, for example, this will make more sense. Okay, this in practical terms now. So see the green like I've shown you before as within linearity, and red means outside linearity. Now I want to give you an example using white cell count, which obviously has happened to me. Okay, so let's say the white cell count is from 0 to 400. That means the linearity, in other words, the comfort zone of the analyzer to give you a result is 400 times 10 raised power 9 per liter. What it means that if you get maybe 0, or if you get 2, or if you get, that's not a problem. But once you start getting something like 500, 600, 1000, because it is now outside the linearity, are you getting me? The analyzer cannot give you a reliable result. Okay, and it is at that point you would have to do something about it. Okay, right. So now, outside the linearity, for example, the patient now is 520. Remember, within linearity is up to 400 times 10 raised power 9. But now you are getting a patient that is 520. This 520 that you are seeing, okay, even if the result gives you maybe 520 or whatever, maybe anything it might give you, okay, that thing is giving, the analyzer is also going to flag that result it's giving you is outside the linearity, is outside the comfort zone, it's outside the specified range that that analyzer is consistent with, that is directly proportional to that very analyzer. So what are you going to do? So this is a workflow. So you have the result of this. What do you do? Like I've mentioned before, you dilute the sample. When you dilute the sample, you then repeat the analysis. And when you repeat the analysis, you apply the dilution factor. What I mean by that is that, of course, the analyzer is going to help you to do this. This modern analyzer will do all of this for you. But for your perfect understanding, so if you now do 1 in 2 dilution, you have to multiply by 2. Okay, if you do 1 in 4 dilution, you have to multiply by 4, and so on and so on. So that is what I mean by apply the dilution factor. Then you can now report the verified result that you've gotten, because the essence of diluting it and repeating is that you want the result to move from this 500 and something, which is outside the range. Let's say if you do 1 in 1 dilution, for example, here, that means half of it. That means you should expect to get 210. No, 200, and because 500 is supposed to be 250, you're going to get 260, I think, something like that. So if you do 1 in 1 dilution, you get 260, which is going to be within this place. So what do? You just have to multiply. Okay, you multiply it, okay, or times it by 2, as the case may be, and then that will not give you the result, because that dilution will bring the concentration of this very white cell to fall within this very linearity. I hope that makes sense. So when you now do this, you are going to see that that when you do the dilution, it will then help this this 520 you are seeing here to now come down to 4 between here, which will be around 260, something like that. It can now fall within here because the linearity is up to 400. Does that make sense? So if you now get the result that you think is outside the linearity, what do? You dilute and you repeat it. And once you repeat it, because you've diluted it, it will then fall within the range. And then you can apply the dilution. If it is 1 in 1, you then multiply by 2, okay? And then you report the result. I hope that makes sense. Okay. Now, let us also look at this very example using creatinine. So let's say this creatinine measuring range is between 20 to 1,500 micromole per liter. But the patient result is greater than 1,500. So what are you going to do again? The same thing. If it does give you a result, you can't rely on that result, because the result is outside the linearity, is outside its measurable range. The key word for linearity is over a specified range, over a measuring range. The same thing is applicable with the calibration, is a range. So analyzer gives you a result using a particular range. So once the result fall within that range, that is within linearity. Once the result is outside that range, that is outside linearity. So it's not enough to know what linearity means. You also need to know what to do when your result fall outside the linearity, and that is what I'm walking you through now, that you need to do a dilution. And in most cases, analyzer is going to do that for you, okay? But that's by the way. So let's say under creatinine is 20 to 1,500, but the result you are getting is greater than 1,500. What do you need to do now? Because the result exceed the linearity of the analyzer. So what are you going to do? You dilute, okay? When you dilute, you repeat the analysis and then you measure, okay? So when you measure this, let's say you get something like 800. So this 800 you are getting now, you see now, is within this very 20 to 1,500, because 800 is no longer up to 1,500, and you then have to multiply by 2, okay? And then the result will then become 1,600. You see now, this 1,600 you got, although is above this 1,500, but it is more reliable because you have diluted the concentration to fall within this linearity. Now, because you have diluted it and it fall within this linearity, it then gives you confidence to multiply based on to multiply with the dilution factor. Let's say 2 or 4 or 5, depending on the dilution that you have done. So that is the whole essence of understanding linearity and what to do about it. I hope that makes sense. Okay, fab. Now, as I try to bring this now to a close, you are going to see that, imagine that these are different departments: hematology, coagulation, biochemistry, immunology, as the case may be. So it doesn't matter, anything that is outside the limit of the analyzer, okay, anything above the limit of the analyzer, you dilute and repeat it, okay, whether it is white blood cells, factor 8, okay, or creatinine or ferritin. Once they are outside, what do? You do dilution. Sometimes if you do 1 in 1 dilution, like for example in in factor 8 now, of course, in other things as well. If you do 1-in-1 dilution and it's still outside the linearity or outside the range, what do? You do 1:1, you keep increasing it. So wherever you are able to now bring the concentration to fall within the range, what do you then do? You multiply. Does that make sense? So you are multiplying it based on how many dilution that you have done, whether 1:2, 1:1, 1:4, 1:5, 1:6, as the case might be. Okay. So, but that is the whole essence of it. So if you do a dilution and let's say 1:1 dilution and the result is still outside the limit, what do? You do a further dilution. That is what I mean by here, further dilution. So you do dilution. The whole essence of dilution is to bring it to the specified range that the analyzer is consistent with. I hope that makes sense, guys. Okay. All right. So please feel free to let me know what you think about this video. And of course, do put a comment. Let me know if you do have any question. If there is something that you are unclear about, please feel free to let me know. And I'm more than happy to answer the question for you. Okay. All right. Thank you very much. Till I come back your way again. Don't forget, subscribe if you have not done so. And of course, maybe I should use this opportunity to also let you know about this book that I've written. Feel free to get this book on Amazon, and I'm sure you are going to enjoy it. All right. Thank you very much. Till I come back your way again. Bye-bye.